All right, so problem number 9. We've got this modified Atwood machine, but it's inclined, and they want to know the acceleration, the tension, and then what does it mean in C when they say the system to be in equilibrium? What does that mean?
Like not moving.
That would be static equilibrium. Static means not moving. But so if you're not moving, it can be in equilibrium, but not necessarily, right? It means not accelerating or not changing your motion. So, like something that's not in motion but isn't in equilibrium would be like throwing a ball up right at the top. It's not moving, but it's still changing its motion. So equilibrium is not accelerating. Static equilibrium would like to be my calculator right there, which is not accelerating and not moving. So they actually probably mean more static equilibrium than equilibrium. But all right, so I think rather than trying to draw that for at least the force-free one, first one, I'll grab it instead. How many force diagrams am I going to need for this problem? 3, because, I've got the system, and then I have each of the bodies in the system. So, on Monday, on your in-class problem, I would expect 3. So, all right, so I've got my system there, and then draw the box here, and then the other box here. Let's see what they give me for inertias. M1 is 10 kilograms. So this is 10 kilograms. M2 for me is 3.1. So that means my system is 13.1 kilograms. In looking at this, because my heavier weight is hanging off the end, I'm going to predict that it's going to accelerate counterclockwise. All right? Now, the nice thing is if I guess incorrectly and it actually accelerates clockwise, when I do out my mathematics, I'll just get a negative answer for my acceleration. And whoops, I picked the wrong direction. But the value will still be the same. So, kind of not a bad situation. So, in the system, we have the weight of 1. We have the weight of 2. I'm using a different color because they're different directions than each other. We have the normal force of 2 on this, and then we have an acceleration in that direction, which I'm going to show is also curved that way. So here, that acceleration would be downwards. Here, it's in the same direction, it just points differently. Kind of a weird statement, but here we have f g1 again. Here we have f sub t. Here we would have f sub t. There's no friction, so I don't have to worry about that. Here we'd have force normal caused by the second object, f sub g of the second object, so the weight of the second object. Yeah, so those would be the complete force diagram. What I'm going to do just below this, just to get math out of the way. The only thing that's in in two dimensions is that FG2. So I'm going to right away resolve that into its parts, and I would have FG2 down this way. I would have one part points this way, and the other part that points that way. This angle here, it's the same as my angle theta with the horizontal, and for me that's 34 degrees. So this is 34 degrees, which means that this side is FG2 sine 34 degrees, and this side is FG2 cosine 34. And they assume the x positive direction is down the inclined plane. So they've actually asked me to make the direction that I picked my acceleration in to be negative. All right? So, but I think they're just asking for magnitudes, aren't they? So we have to be, so we'll take their direction of down the plane's positive because they want the sign in the acceleration. So we'll go with their standard. All right, so the one I think I'm going to use is the system to tell me about the acceleration of the system, because while acceleration is in all three force diagrams, the only one that has things that I know compared to things I don't know is the system. Otherwise, there's this tension in there, which I don't know yet. So I'm going to go with the system here first. So let's go system. And in here, of course, start with your one and only equation. As yesterday, I'm going to draw that equation first. My inertia here, 13.1. And let's see. I'm going to have FG1 in this direction. This is where it gets really weird. FG2 sine 34 degrees in that direction. Force normal 2 in that direction, and FG2 cosine 34 degrees in that direction, and my acceleration is going to be that way. Well, the strangeness up here in my diagram is that I have this directionality of counterclockwise. So if I'm accepting that the two masses are moving in the same direction because they're in a system, and a system can only move in one direction at a same acceleration. So I'm accepting that up the plane and around the corner is one direction. I'm looking at this M2 moving up the plane, or at least accelerating up the plane, and I said, oh, the normal force is perpendicular to the plane. So I drew, so FG1, if I'm drawing it down, I have to draw F normal 2 perpendicular to that. So I kind of said, I'm going to go with FG1, that direction, that I called clockwise in the diagram, as being up and down. And then perpendicular to that, we'll just go across. Because this is really a representation. It's not like that one points down and that one points this way. I established a direction with FG1, and then I looked at what direction are other things in relation to that. The normal force is perpendicular to that direction, and then I actually used my triangle here to say, well, and I wish I had put a third color here. I'll go over this, so red and green together there. So FG2 is in both directions, that counterclockwise direction and perpendicular to that, whatever we want to call that. So I took the part that is parallel to the clockwise, to the counterclockwise, FG2 sine 34, and put that in its correct orientation, and then did the same thing with the component that was perpendicular to that direction. So I could actually spin this thing any degrees, as long as the ones that I've labeled in blue are parallel to each other and perpendicular to the ones in green. And that is kind of the hardest part to conceptualize. Sometimes another way that I've done it to help myself kind of get my head around it is to take and warp this force diagram into another way I think about it. Because M1 here is I think of it as being pulled down by gravity, right? So, what if instead of gravity, it was being pulled by some big force? And then I could picture this. M2 sitting on a surface, attached to M1, which is kind of hanging out here in the air. And then M1 is being pulled this way by this force that I'm calling FG1, which has the same size as its weight. M2 then would have a normal force up that way, and its weight, just because of the weirdness of it sitting, is pulling in that direction. In my mind, yeah. And that's probably the hardest, most abstract part of this, is trying to wrap your mind around this. Going around a corner is one direction, because that can be boggling. Okay? But yeah, in my mind, I actually do this. And that's what I picture when I start looking at it, which hope may or may not make sense to you. So when I draw these, like on my own paper I actually draw them in that orientation rather than this orientation. Yeah. All right. Good. Weird. Good. So now that I've drawn my equation, I can fill it in mathematically, right? I'm going to go with just do the blue part because that's the direction my acceleration is in, and hope I get lucky. So we were they said take down the plane as positive, so that means that this direction we have to take as positive. All right? Yep, I think that's right. Hopefully, it's Friday after all. That means we've got FG2 sine 34 degrees minus FG1 equals the inertia, 13.1 kilograms, times A, which is negative A. I remember that weight is mass times the gravitational field strength. So I have M2G sine 34 degrees minus M1G all equals negative 13.1 kilograms times A. So my M2 was 3.1. So I have 3.1 kilograms times 9.80 newtons per kilogram. Sine 34 degrees. Minus 10 kilograms times 9.80 newtons per kilogram. That gravitational field strength all over negative 13.1 kilograms equals A. Now remember, I'm solving for the magnitude of A. If I pick the right direction for it, I'm going to get a positive number. But we know that it moves in a negative direction. Let's see. 3.1. I get an acceleration of 6.18 meters per second squared, and I got a positive number which tells me, hey, you picked the right direction. It should be in a negative direction. So let's see if that's right. Nope. What did I? Oh. I forgot. It should be in a negative direction. So yay. Any questions on that before we, Alright, so part B, the tension in the string. Need to go back up to our force diagrams and pick which body we're going to use to find the tension. Can't use the system because the tension is an internal force. So we're either left with the hanging mass M1 or the mass on the incline M2. I go with the hanging because then I don't have to do any trig, right? So I'm using the hanging mass here, M1. I'm going to start with my equation. Draw my equation, otherwise known as a free body diagram. All right, so I have an inertia of 10 kilograms. I like to write it next to it. Fg1 down, Ft up, acceleration down. Now take that pictorial filling in of my equation and use mathematical symbols instead. Still taking. Should we stick with the convention of up is positive or go with down is positive? Does it matter? We'll stick with up is positive. So I would have Ft minus Fg1 equals M, which is 10 kilograms, times a negative A. Oh, wait a minute. I know what A is. Negative 6.18 meters per second squared. Ft is Fg1 plus, minus, because it's plus a negative, 10 kilograms times 6.18 meters per second squared. And I can fill in from there, right? This would be 10 times 9.80 newtons per kilogram minus 61.8 newtons. And I should be able to find F sub t from there. Right? And for mine, I get 36.2 newtons. Hopefully you got something similar. Any question on that before we bounce along to part C? Mine was 36.2 newtons. What value of M1 will the system be in equilibrium? And so we had said that equilibrium meant that the acceleration was 0. So if we go back to our system here, now, and look at it, if we change that acceleration to 0, then that would be the situation when it's in equilibrium. All right? So, using the same idea, I'm not going to bother doing a new force diagram. I don't think it's going to show me anything new. But if I take all of this that's here for the system, but set A equals 0, I can do it the exact same way. I get down to here, and this is just for ease. See if I can close that and write it down. So we have all of that same idea behind that we did in part A, except now the acceleration is 0, which means that we end up here being able to simplify a little bit to m2g sine of 34 degrees is still there. If this is 0, that means that whole side, the right side is 0, so this must equal m1g. So divide both sides by g, and the g's cancel, and you're left with m2 sine 34 degrees equals m1. And they asked for what would be the value of m1 that would bring it in. So we're going to do number 10 here. And in 10, we have very similar to number 9, which we were just working on, in that we have a modified Atwood machine again. The difference here is we have kind of a simpler idea in some cases, some ways. Oh yeah, much simpler idea here that we don't have the incline, so we don't have to worry about the kind of, we have that trig involved here also. And we don't have friction, which is the other way that we could have made this a little more complicated. So let's capture that image, and then, oops. Should be an exchange that came out there. Let's see what it came out. Okay. So again, how many force diagrams am I going to need? 3, because I got the system plus 2 bodies. So, do my system one. Do a dotted line. Then I'll have M1 and M2. Let's see what they tell me about these guys. M1 is 41.5. So this one is 41.5 kilograms. Ran out of room for kilograms. M2 for me is 13.6. So that means that I'm at 45.1 kilograms for my system. 55, excuse me. 55, right? Yeah. 55.1 kilograms for the system. All right, and no friction. So, let's see. I'd have a different color. Again, which direction is this going to accelerate in? Right, clockwise. So, forces that are in the direction of that acceleration I'm going to do in blue, which would be FG2. And forces that are perpendicular to it, just for my own organization, I'm going to do in green. Okay, so there is the correct force diagram for my system, or my individual blocks. Now, it looks very similar to last time, except for the fact that we have it a little less complicated. FG2. So those are the correct force diagrams you need for this problem. Any questions on any of those before we run along? Alrighty. So it'd be good to know what they want. Acceleration and tension in the cord. So for the acceleration, I'm going to use the system again. So I'm going to start with my equation. Kind of nice only having one equation. Draw my equation. Fill in my equation mathematically. Oops. What was that? Inertia, 55.1. Realize that the weight of 2 would be M2 G. Right? Any questions on that one before we go on to part B? All right. Part B, we want us to find the tension. So again, I'm going to start with my equation. Fill it in graphically. I'm going to use the hanging mass So the hanging mass FG2 had an inertia of, what was it, 13.6. So I'm using the far right hand there. It's an inertia of 13.6 kilograms. FT is up that way. Acceleration is down that way. Filling that in mathematically. And then I would know the value of A from doing it in the previous part. I end up FT equals 13.6 kilograms times A plus M2G. And solve for that. Very similar to last number 9, except you don't have that incline, so you didn't have to break up the weight of the object on the plane. Folks, don't forget your acceleration points down. So when you substitute in here, because your A is pointing down, you're going to actually substitute in the negative value of it. Can't forget that a vector has directionality. Alright, so we're going to try number 11 here. And grab it. Kind of ironically, we're going to end up again with 3 force diagrams. It's a system with 2 bodies. So and let's see, my inertias are equal. Yay! 3.2 kilograms. That means this is 6.4 kilograms. And I would have, let's see, I would have the weight total down here. T1 up. Here on M2, because, I should draw on my chords. Downwards here, I'm just going to have F sub G2. Upwards, I would have FT2. Sorry, and I should have labeled this FT1. Here, let's see. Here I'm going to have FT2 down, FT1 up, but also the weight of number 1 down. Oh, this is like the one we did in the packet, right? Except I had 3 rocks rather than 2. Oh, good. and also the one in the packet didn't have it accelerating. Here we're accelerating down. And then we have the acceleration up. So in the first case, we're going to have in all of these an acceleration down. And technically, we should draw new ones for the second and third situations, but we'll make do with these. Excuse me. So let's look for the top tension first. I'm going to use the system to find that. So, start with my equation. What's the next step? Oh, come on, folks. I've done it 7 times this block. What's the next step? Free body. Fill it in graphically. Then, same mathematically, ft1 minus ft total equals my mass total times my acceleration. So ft1 equals m total g, oops, this is negative, minus m total a. I know m total, I know g, I know a, so solve for ft1. Then I want to find the tension in between them. So as before, start this way. Draw my free body. I'm going to do it for the bottom rock. So I'd have FG, what, bottom rock 1 or 2? 2. So I'm going to do it for the bottom rock here. FG2, FT2, accelerating downwards. Hopefully you see that free body, that filling in of the equation, very identical to filling in the equation up there. So hopefully at this point you can translate that mathematics over, right, from pictorial to mathematics. For part B, you're now accelerating upwards. So all that's doing is changing the directionality of your acceleration in these drawings and in the mathematics. So flipping it, changing it from negative to positive. But the same setup, same exact locations of our forces. Then for the last part, the maximum tension of the two strings to withstand is this. What maximum upward acceleration can the elevator have without having one of the strings break? So, looking back to our force diagrams, which string is under, do you predict is going to be under a greater force? The FT, the one at the very top, or the one in between them? The top one. So, to do part C, you need to look at your answers for A and B and see which one is creating a greater tension in the top string. And then, in that case, go back to your free body, and you don't know A, but you know FT1 in that case. So it's the exact same setup, except rather than knowing A, you know FT1, and you're solving for A. So why don't you guys work on this one kind of, with your group or by yourself, and if you have problems, just let me know. I'll go over, give you a hand, point you in the right direction.